Recording here. So we have. You want me to sit somewhere else? Or are you good? Okay. I can sit right there if you want me to. Maybe I will sit there. Okay. Solubility. So Ksp. So this is just the equilibrium, or this is K for solubility products. So you've kind of been lied to for the last couple of years about how things are insoluble. They are mostly insoluble, but there is some solubility going on in there, just a little bit. But it's so tiny that it doesn't, we just kind of don't talk about it. But it is there. We're going to mathematically look at this. So if you need your explanation, there it is. So the big thing is you're going to take your solid, and we're going to take our solid and we're going to break it up into its two ions. Okay? And we're going to put it into a rice table and then do some calculations with it. You see here you have a bunch of solubility constants. Solubility or Ksp constants. If you look at those, what can you say about those? What can we say about those Ks?
They're small.
Very, very tiny, right? Really small. What's the smallest one there?
38.
The sulfides. I see a 10 to the minus 52.
10 to the negative 41.
52.
The silver or mercury sulfide.
Yeah.
So these are really small. So it's not going to shift much to the right. It's really going to be shifting to the left. So we could say that the smaller the Ksp that you have, then the less soluble it's going to be. Okay? So if we have our solid and it breaks up into its ions, we're going to see shifting to the right. What?
Smaller Ksp means what?
Less soluble. Okay, so let's just jump in here and do a problem. Calculate the Ksp for the following salts using the information provided. The concentration of CrO4 2- in a saturated solution of silver chromate is 5.5, or is it 6.50? Or is it 5? 6.50 times 10 to the minus 5th molarity. So the very first things you want to do, especially when you see that you have this solid solution, the solid here, is let's go ahead and you're going to take your solid. So we're going to take AgCrO4 and we're going to put it into a rice table. And we're going to take silver chromate and we're going to break it up, I forgot a 2 in there, into its ions. So what 2 ions will we get? Ag, no, it's a +1. So it's going to be 2 of them, plus CrO4 minus 2. So we have our I, C, E. Initial concentration of our solid. It's a solid. Nothing's going to be there. We haven't dissolved any of it yet. We're just now putting it into water. So initial concentration of our silver and our chromate is 0. So what can we say about the shift? Which way is it going to shift? If it's solid, then we're going to shift we're going to go to the right because we have nothing there. Oh, that should be 2x, huh? So at equilibrium, our equation is 2x and x. And they've given us, what have they given us? They said the concentration of CrO4 is 6.50 times 10 to the minus 5. So this is 6.50 times 10 to the minus 5 is my x. So 2x is going to be 1.3 times 10 to the minus 4th. Now we can solve for KSP. So write your equilibrium unsubstituted expression. So KSP is going to be equal to CrO4 2 minus times Ag minus squared. What? Oh, plus, yes, thank you. Why is there no reactants in it?
Because solids don't count.
Because solids don't count. All right, so now we have 6.5 times 10 to the minus 5. And we're going to multiply that by 1.3 times 10 to the minus 4 squared. And what do you get for that? To 3 sig figs.
How many?
3.
It's like 1.10.
1.10 times 10 to the minus 12.
Yeah.
And our units, there are none. And that is it. Questions? All right, the next one. The solubility of AgBr4 in water is 7.2 times 10 to the minus 2 grams per liter. So there's grams per liter. One thing I want you to know is anytime you see the word solubility, the solubility of something, that is our X. Okay? They've given me my X here, except for, what's the problem? It is in grams per liter. So we need to take our 7.2 times 10 to the minus 2 grams in 1 liter and change that to moles per liter. And for every 1 mole, there are 235.76 grams of silver bromate. And I get 3.1 times 10 to the negative 4 molarity is our X, which equals our solubility. So now we can solve for KSP. So go to your rice table, say silver bromate, and break it down into what? It's ions, Ag plus 1 plus BrO3 minus. Initial, so we have X. Initially we have nothing. It doesn't say anything about us having anything there, so it's nothing. Which means we're shifting to the right. So we have X and X. And we just solved for X. We know that X is 3.1 times 10 to the minus 4th. So now we can solve for our KSP value. Yes. So KSP, get your equilibrium expression, is equal to silver times bromate is equal to 3.1 times 10 to the negative 4 squared. And what do you get?
9.61 to the negative 8.
9.61 times 10 to the negative 8. Easy? Sure. Another? But this time we're going to solve for x rather than KSP. All right, concentration. Calculate the KSP for this. All right. Oh, wait, hold on. Where did I go? Oh, that's the same one. Duh. Calculate the solubility of barium carbonate in 0.5 molar. Did I skip another one?
Yeah.
Oh, my goodness. There we go. Now we're on track. Calculate the solubility of the following compounds in water. Calculate or use the solubility product constant in your textbook. So first of all, we need to go find KSP. So go back to that table and tell me what is the KSP for barium carbonate and what is the KSP for silver sulfide.
Barium carbonate is
2 times 10 to the negative 9. And then Ag2S, 1 times 10 to the negative 49. All right, so we know KSP, 49. So our very first step is to take barium carbonate, BaCO3, and we're sticking it in the rice table. And we're going to break it up into its ions. Ba2 plus CO3 2 minus. Initially, we have nothing of barium and of carbonate. The shift or the change is going to be a plus X and a plus X. So at equilibrium is our X. So we have to go find X. So get your equilibrium expression. KSP is equal to barium concentration times the concentration of carbonate. And now substitute everything that we just have found. We know that 2 times 10 to the negative 9 is KSP is equal to X squared. So what is X? X is solubility, right? And the value of that is 4.47 times 10 to the negative 5. And our unit is molarity. Good? Do one more. All right, silver sulfide. Silver sulfide. First thing you do, write your rice table, Ag2S. Break it into the two ions, 2Ag plus S minus 2. Solid is out of there. Initially, we don't have anything of either one. Our change is going to be plus 2x and x. So now we can go write our KSP expression and solve. AG plus squared and S to the minus 2. 1 times 10 to the negative 49 times 2x squared times x, which gives me 4x cubed, and solve for x. So x equals our solubility, which equals what value?
So, you can test it after what solubility.
You don't. I'm just putting that there to reiterate to you guys that that's what x is when we're talking about KSP.
Bucket split. Okay. Should we do a quadratic thing?
Nope.
You can't do quadratic. Oh, sorry.
So it's what, 2.92 times 10 to the negative 17? Units is moles per liter, or big M. Any questions on that one?
That one would also shift to the right.
Yes. There should be a plus X over there.
Why is it? I see.
Okay, so now I'm going to change it up on y'all, because it can't be that easy. We're going to go ahead and cross this one out. We're not going to do this, the B, 15B. Calculate the solubility of barium carbonate in 0.5 molar barium nitrate. So the difference between this one and the last one was we dissolved it in water. This time we're dissolving it in barium nitrate. So this is what we kind of call the common ion effect, because we're dissolving it in something that has the same kind of ion that of what we are dissolving. So the common ion here would be barium. Okay? So the very first thing is we can go ahead and just start our rice table like usual. So we have barium carbonate, and it's going to break into barium 2 plus CO3 2 minus. Is everybody okay with that? Now initially our solid still gets crossed out. So initially we are dissolving this not in water, we're dissolving it in barium nitrate. So initially, how much barium are we starting with? 0.5 molar. And we have no carbonate. So now, our change is going to be still plus X. And at equilibrium, we're going to have 0.5 plus X and X. Our KSP on this problem a while ago was what? 2 times 10 to the negative 9? So then we go in and we solve our KSP expression. So KSP is Ba 2 plus and CO3 2 minus. And then we can solve. Now the beautiful thing about this is what we can do with X. So I learned it this way, and what we do with X is what we say we trump it out, okay? So, and the story that one of the ladies that I learned this from is here's Trump walking down the street, right? And he drops a dollar bill. And how much is that going to really affect him if he drops that dollar bill? How is it going to affect his wealth overall? It's not, right? He's probably not even going to care about it. The solubility in these is so small that X is negligible to us when we're looking at it with that 0.5. So what you can do is if you say X is negligible or we're trumping out X, you need to write on there that X is negligible. Okay? You want to make sure that the AP readers know that that is negligible and you're not just crossing it out to cross it out. So now we can go substitute everything into our expression. So 2 times 10 to the negative 9. And then we have barium, which is 0.5 times X. And we can solve for X. .0 times 10 to the negative 9 molarity. And that is our solubility. Okay, because we know that this is very, very small, we can go ahead and get rid of that X in that equation to keep us from going to quadratic. Now, what happened to our solubility when we went from water to dissolving it in barium nitrate? Our solubility prior to doing this in water was 4.47 times 10 to the minus 5, and now it's 4 times 10 to the minus 9, so it's gone down a lot, okay?
So would it be wrong if we had still gone like the quadratic route?
No, you can do it. It's just they're not going to do that because, again, quadratic equation and calculators and all that. So, and then there is a rule, a 5% rule, and we'll talk about that in acids and bases.
Would you be within 5% of the
It has to be, like, if it's anything less than 5%, then you can say it's negligible. Okay. Another one. This time, though, a 45 ml of 0.015 molar calcium chloride is added to 55 milliliters of sodium sulfate. Is a precipitate expected? Explain. Your answer must include a calculation. So when you see something like this, you have 45 mils added to 55 mils and all this stuff. Think of dilution. All right, we're diluting something. So the very first thing we're going to do, just like we did, so calcium chloride and sodium sulfate. When those two come together, what are we going to get? Sodium chloride and calcium sulfate. So calcium sulfate. And we know calcium sulfate from our solubility rules is insoluble, but we want to see what its solubility is. Okay. So now we're going to break that down into Ca plus 2 and SO4, 2 minus. And we want to know what is the I. So we have the I. What's the initial concentration of what we have? Well, we diluted it. So we need to start with calcium. How much did we come in with calcium chloride? It was 45 mils. So we're doing an M1, V1. So MV equals MV. We start out with 45 mils, and our volume that's our volume. Our molarity is 0.015. When we diluted it, we do not know what its new molarity is, but we do know what is our total volume. We added 45 plus 55, so 100. So solve my x for me. .00675. All right, so that's the initial concentration of calcium. We go and do sulfate. Sulfate was 0.01 molar, and we had 55 mils. We're looking for its new molarity and its volume of a total of 100. So X is what here? Is it 00? 0.0055. All right, so now what's next? Which way does it shift? Can we determine which way it shifts? What do we have to do to determine which way it shifts? Q. So what is KSP? Does it tell us? I'll go back and find us what KSP. I'll go ahead and let you guys. KSP for calcium sulfate is 3 times 10 to the negative 5. So we need to find Q and compare it to KSP. So Q is going to be equal to calcium times sulfate. And that is going to be 0.00675 times 0.0055. So what is the value for Q? .7 times 10 to the negative 5th? Okay, so how is Q related to K? K is 3 times 10 to the negative 5th. Q is 3.7 times 10 to the negative 5th. Q is smaller or greater? It's greater than K. So we're going to shift left or right? We're going to shift to the left. If we're shifting to the left, then what's going to happen? Are we going to form a precipitate, yes or no? Yes. Because we're going back towards the solid. Okay? So yes, precip forms. If it would have shifted to the right, we would have had no precipitation. Everybody good with that? All right, so now we're going to do the big mama AP question. So this is a former AP question. 4 parts. You're going to see that they build upon each other. It's going to go from easy to hard. So the very first one says, write the expression for the solubility product constant, KSP. So first of all, let's write the KSP here. So KSP is going to be equal to concentration of Mg times F minus squared. That is 1 point right there. And then calculate. Now calculate the KSP from this.
I'll just quit.
So we're going to go ahead and do our Rice table. So Mg F2 breaks down into Mg2 plus 2F minus. Our initial, Marcus. Our initial concentration So solids out, initial concentration is 0 of everything. Our change is going to be a plus x plus 2x. And at equilibrium, we need to know what our solubility is. And it says our solubility is, so that is x, is 1.21 times 10 to the minus third. So we're going to plug that into our equilibrium expression. So Ksp, and we've already written it once, so I'm not going to write it again, is equal to 1.21 times 2. 2.42 times 10 to the minus third squared times 1.21 times 10 to the minus third. And what do you guys get for our Ksp value?
Wouldn't that be squared root?
I squared one of them, so it's actually cubed. Temperature right now, it's still at, it tells us at 18. So right now we're still at the same. We haven't changed. Did you get 7.09 times 10 to the negative 9? So that is Ksp. That is your second point. Everybody good with that? Now calculate the equilibrium concentration in 1 liter of saturated MgF2 at 18, so we're still at the same temperature, in which 1 mole of solid Kf has been added. So now what have we done? We have MgF2, and we've added a common ion, and our common ion this time is Kf, so it's going to be F. So our initial is still 0 for magnesium, but for F, I've added 0.1 molar in there. Change is x plus 2x. And then we have x and 0.1 plus 2x. And we need to solve for x. So, what is our Ksp at 18 degrees Celsius? Didn't we just solve it? 7.09 times 10 to the 9th is equal to x times, and here, trumping that out, so I have that times 0.1. No, it's just because it's so small that this is solubility constants, and so they're so tiny, we're assuming that they're negligible. 0.1. So x, which equals my solubility, is what? Which equals the concentration of Mg2 plus. Eighth? I got 7th. Oh, that should be point.
Squared.
Oh, squared. Sorry, Kidron. -7. My fault. All right, so let's do the last one. Or there's the next last math one. So we have predict whether a precipitate will form when we have 100 milliliters of 3 times 10 to the negative third molar mixed with 200 milliliters. So now again we have another M1V1. So again we start with MgF2, Mg2 plus 2F minus. And we want to know if a precipitation is going to form this time. So initially, we have 100 mils of magnesium times 0.003. And that's going to be equal to M times 300. So my molarity is going to be 0.001 for my magnesium. We do the same thing for our fluorine. So 200 times 0.002 is equal to 300x, and x equals 0.001. So, and then we put those into our, so then we have to decide which way does it shift? How do we know which way it shifts? If a precipitate's going to be formed or not? No, what do we need to do? Find Q. So Q is going to be 0.001 squared, which equals 1 times 10 to the negative 9. So how does Q compare to K? Negative 6.
So Q is
Oh, wait, sorry, that should be cubed. The F is squared, sorry. That's what I get for skipping a step. So 1 times 10 to the negative 9. So how does Q compare to K? It's less than K, so it does a precipitate form. No precipitate. And our very last one does not add calculations. At 27 degrees, so we were at 18 degrees, now we've gone to 27 degrees. So at 18 degrees, what was our KSP? Our KSP was, oh no, wait, hold on. At 18 degrees, our solubility. Our solubility was 1.2 times 10 to the minus 3. Now, when we go up to 27 degrees, our solubility goes to 1.17 times 10 to the minus 3. Is the dissolving of MgF2 in water an endothermic or exothermic process? Give an explanation to support your conclusion. Okay, so what was that explanation?
Oh, yeah, I see.
What? So say it.
Exothermic, because it's giving off more heat, even though because it's losing its molarity, or it's giving off heat.
And so which way did we shift? We shift to the left. Good. No calculations involved. So as we added heat, it shifted left, which means that our solubility went down, so it's exothermic. So heat was a product at that point. Any questions? All right, so your homework tonight is that last page. And then